It wasn't like it was just a PC thing. In the US, that might have been the most common type of machine they would run on, but you'd also find BBS software available for Amigas, Apple Macs, even some of the common home 8-bit platforms were used as machines to run BBSs, although those are quite few and far between. But I certainly know of at least one BBS that was run from a Commodore 64 and a couple of floppy disk drives, although most would have considered having a hard drive as kind of the base requirement for running a BBS. You would also see people using BBC micros to run video text systems, which are related to BBSs, but not quite the same. I'll cycle back to those in a bit. The local BBS I used when I was a kid was run using an Amiga 500 and a GVP A530 accelerator and hard drive, which gave it 4 whole megabytes of memory, 68030, and of course a fuzzy hard drive. And to me that BBS was an invaluable source of information and also utilities, as is unlike the internet then. It also provided my first experience as well. A sort of email, again we'll come to FidoNet a little bit later on. Now my local BBS back then was quite posh in some regards, in that it had 4 whole modems and 2 ISDN lines. Now goodness knows how he attached those to an Amiga 500 because it's got 1 whole serial port. I'm guessing he must have had some form of multi-port serial card plugged into the GBP's little expansion bus thing. Although it's something he must have created himself or got someone to do for him, because I've not been able to find a commercial offering that provides that option for the Amiga 500 or the GBP expansion port. Most BBSs typically had either 1 or 2 modems, with the large BBSs with more phone lines, typically running on a PC, because it was a lot easier to add more serial ports to a PC than it was to most other platforms in a cost-effective way. So how does the connection between you and the BBS work? Well, you'd use whatever your chosen computer was, attach a modem to it, dial up the telephone number of the BBS. The BBS software at the other end would get an indication of ring on the modem and would answer the call. From then on out, the connection works, well, basically the same as a dumb serial terminal, like a BT100 for example. In fact, if you connected the modem to a serial terminal and didn't mind typing in the AT commands to make it dial, you could actually use a dumb serial terminal to connect to a BBS. Once you're connected, what's sent down the line is the text characters for your terminal software or terminal to display, as well as some escape sequences that might do things like change the current color selected or swap you into using character graphics mode. In fact, most BBSs would use what is known as the ANSI escape sequences to control the user's terminal. Some would also offer a dumb mode where it uses almost no control characters at all, so that older terminals or terminal software can connect to it and still work more or less well enough. In fact, you can even connect up with a teletype machine, although both experiences would be very monochrome, one would be a bit noisier than the other. Now this via terminal approach worked extremely well for the main bulletin board software, where on almost all of them you can navigate to different notice boards or threads if you like, where you can post and read what other people are posting. The structure to this is very similar to how forums are built today. Also, like forums today, you get the option of direct messaging between you and the other users on that BBS. And this is one of the reasons why having a hard drive kind of became the entry-level requirement for being a BBS, as these messages could get big and relatively quick access, or at least compared to the size and access speed of the floppy drive. And this became especially true when BBSs started to give away to distributed software. Now, you may be wondering, given the description I've given you as how this works like a terminal, where does the whole software downloading part come in? How does that work? Well, for that we use something called X modem, and then later on Y modem, and finally Z modem, although to be honest, even by the time we had Z modem, X modem had not gone away. X modem was originally developed by Ward Christiansen in 1977 for his CPM-based terminal software, modem.asm. Now some of you have just noticed me bringing up CPM then, and of course in the early history of bulletin boards, CPM was the phone dominant for a while. After all, almost every machine you could buy that ran an operating system ran CPM, at least until that became not true. Anyway, back to X modem. X modem was a protocol for doing file transfer between 2 machines over the modem. Well, in fact, despite the name X, the modem bit is off all you had a modem cable between 2 machines per file using X modem. X modem would transmit a series of 138 byte data blocks, each wrapped in a packet with a header and a single byte checksum at the end of the packet after the data block. The reason the data block was 128 bytes is that's the same size as the default block size for floppy disk CCPM. The header's basically 3 bytes. The first byte was control code 1, or startup header, which is an ASCII control code, and that's not something that really comes up very often, hence the reason for using it. The second byte would be the block number, that weirdly would start at 1, not 0. The third byte was then the inverse of the block number. You then get your 128 bytes of data, followed by the checksum. When the machine on the receiving end gets that packet, it calculates out the checksum for the data it's received, and checks it matches the final byte of the packet. If it does, then it can send back ACK, and the machine sending the data can send the next packet. If it doesn't, it sends NAC, and the sending end would just resend the same packet, and the receiving end would go through the same loop again. If it continually sent NAC, well, eventually the operation would just time out, and we drop back to being a regular terminal again. Once the file transfer was complete, you'd send EOT, end of transmission, and you could just go back to being a regular terminal again. Now, those of you who are mathematically inclined will have realised that a 1 byte checksum is not really enough to spot all the errors that might occur in 128 bytes of data. So it would not be uncommon for an ex-modem transfer to fail in a way that the system didn't detect and just moved on. You just ended up with incorrect data in your file. You may have also spotted that there's absolutely no mechanism to abort a transfer whatsoever. Once it's going, both ends just just transmit an ACK or NAC until the end of the file. If that's a big file and you decide you don't want it anymore, well, tough. Right? Hang up the modem, dial up again, or wait for the thing to just finish. Now,
just a guide and has no else to say how these
yeah, and again, privacy is early on. The protocol gap why you have. Now, the first thing we added was the abort concept. So instead of being able to just send NAC or ACK, which was the packet that we got, it can send ASCII character 82hex, or decimal, which was CAN or cancel, which would cause the server to abort and stop sending these packets. ACK on terminal notice switch back to normal terminal mode, because it's nothing but send CAN. And probably more importantly, you'd also stop using a 1 byte checksum at the end of the packet, and in fact change to a 16-bit CRC, which would let the receiving end detect any corruption in the packet. Now, it was not the first program to introduce that 16-bit CRC, as there was something called ex-modem CRC that did the same thing. But YAM was the first time we got it to combine the abort concept as well. YAM also let us increase the size of the data bit of the packet to 1 kilobyte rather than 28 bytes, which made transfers a bit more efficient, and assuming we didn't have a noisy line with lots of packet corruption on it. Now, another part of the modem protocol was the batch transfer, although it's fair to say that quite a few implementations of modem kind of failed to notice this bit of the specification and simply didn't implement it, which is why in some software you'll see modem batch as transfer protocols that you can use. Now, this was predominantly used for BBSs talking to other BBSs where you had a number of files you wanted to transfer, which is kind of what the FIDO now thing is. Again, we're going to come back to that later. Sorry, FIDO, let's keep doing that. Now, if you remember before when I was talking about the packet structure, I said that the data packet started with packet number 1 rather than 0, which is fairly unusual. Most things in the world of low-level computer programming, the counting index starts at 0. So this batch transfer took advantage of the fact that data packet 0 wasn't a thing. So it could use data packet 0 to transmit some extra metadata about the file that was being transmitted. So data packet 0 would get loaded up with the file name, create data, modify data, potentially. So the receiving end knew which file it was getting, and you could have multiple exchanges this way. Now, this is where it became a little bit of an issue for line modem implementations that didn't implement this whole 0 packet concept, in that they would just packet 0, go, but it's not supposed to be a packet 0, and send back NAC. Which way the server would send packet 0 again, you could get NAC, and eventually the communication would time out to die. And some software would offer line modem batch mode, which you could use that protocol, it would understand packet 0, and get the file name, ACK it, and then the whole transfer would happen. If you did support this packet 0 concept, it was also quite handy when you were your machine, the file name would be filled in by default. You didn't have to make up your own file name. Right, let's park the history of BBSs there for a little bit, and we're going to get on to the disgustingly modern implementation of that. Now, I said I was going to build a BBS in this video in the most obnoxiously modern way possible, so I should probably dig into what I actually mean by that. Now, I don't want to run a modern piece of BBS software. In fact, I think I want to run a DOS-based BBS application, but I don't want to do that by just firing up either just like a VM or sticking on just a native bit of tin. What I want to do is run some retro software, but in a disturbingly modern way. Try and a modern, outdated kind of an application, because why the heck not? I mean, just because we're running legacy software doesn't mean we have to do it in a legacy way, right? Right? Come the end of this, I want this BBS to be accessible by not only modems, like we would have done back in the day, but also over the internet, because frankly, most of us don't need all they can try to run an actual modem over a phone line. In fact, I may just keep the dial-up bit internal to my house just so that I don't have to pay anyone for a phone line, because the line rentals quite a lot, and I'm pretty sure...
I'm on my way to Solitude to join the Legion. The United Empire is better for everyone.
Let's get to how we're going to run this piece of DOS software. Now, you may have noticed I've not said which bit of DOS BBS software yet, and that's because I haven't chosen the DOS BBS software yet. But I do know how we're going to run our DOS environment. For a start, we're going to use DOSM. Now, the reason for choosing this, not DOSBox, is that DOSM doesn't try to emulate the CPU. I mean, we're going to run this thing on x86, so it's fine. Let's describe which of the application is the real CPU. That's just fine. DOSMU also gives us a pretty decent way to emulate the serial port in a way that puts up to the TCP/IP socket. After all, we're trying to mod, so I want to do serial ports. The other reason DOSMU actually does have a Unix file system inside the DOS environment where file locking actually works properly. So, DOS application inside DOSMU locks a file. That file will also get locked in the POSIX filing system that's been mounted into the Unix world. This lets me fake up those larger environments where you might have more than one PC running BBS software and you can share the files on the network. And having a network.
Always look for fucking caves and treasures behind waterfalls. That's what they always say. That's where the treasures are. They're under the waterfall. They're under the waterfall, man.
And if I think 5-6 years ago, that's exactly what I
yeah, that was pretty good. That was pretty good.
Very thin wrapping between the corresponding device and your operating system, the virtual device within the device of the operating system. But yeah, driving the parallel the operating system that's inside the guest. We also, for quite a while, had some CPU hardware features that meant it's fairly easy to accelerate these workloads. As the operating system in the virtual guest can hit the CPU like it was in 10, doing all the protected mode ring 0 stuff, but it's not actually hitting real ring 0. The processor has a virtualized version of the CPU mix available to it. Now, why VMs gave us a great leap forward in terms of abstraction and how we sort out our workloads, it does come with a problem. You see, each VM is running a full kernel with all its libraries and all the memory and CPU mode that implies having to go to the virtual devices to get access to the field resources of the computer. This is quite a lot of overheads. Normally, we can just run one application inside this VM or service, so it's isolated. We do an applications and programs that make up the service we want to provide to the rest of the world. Containerization simplifies this sort of
I gotta go to the Legion, to the Imperial Legion, though.
really long time. In fact, you can even trace it.
Let this be the forgotten forever. rock and the roll of history. Let it be spoken of by man or mare. We who enter here know this place is sealed by a great price.
We're kind of moving on a little bit from the original Docker model now with things like the container dependency, etc. But we'll stop off at Docker for a minute or two so I can explain how containers actually work. So containers differ from a virtual machine in that with a virtual machine we have to pretend to be a whole computer and run the entire operating system inside of that. With containers, we don't pretend to have different virtual machines at all. We have one machine, real machine, running that kernel, and inside the kernel, and let's just switch to start saying Linux because that's the implementation basically everyone's using these days. So our Linux kernel takes all the structures it represents back to user space, like for example, process table, filing system, tree, sockets, everything a process can see and get out in the kernel. And it has the idea of namespaces too. For every entry in these tables, they get flagged as to whether they belong to a namespace, i.e. on that user space that you see normally, or alternatively, the namespace belongs to a container. If a process in that namespace requests any instructions from the kernel, it will go back to all the entries wanting to the namespace and the container namespaces. If a process looks like it's been in one container namespaces and it's the same request, it will only go back entries that are in the same namespace as it. This effectively allows us to partition up our operating system into multiple containers that can't talk to things that run in but the containers, this model effectively isolates one thing in one namespace and things in other namespaces. Now, Docker took this whole concept and extended it just a little bit further. What Docker added was the idea of a layered file system into this.
Shall never be spoken of by man or mare.
On top of the other. So you could have, for example, a base filing system that's a simple CentOS 7 installed, for example.
What?
Then layer, for example, a web server on top of that, Apache.
Wait.
On top of that, you then layer your PHP install, and then finally on top of that, the PHP application you want to run. Now, what Docker did was give us tools so that we could build these layered filing systems and also store.
Bear well snake, 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 bear whale 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 snake,
File system. Docker also takes in that image.
Bear whale snake.
What is the thing that currently runs?
Bear whale snake. 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 Bear whale snake.
Or extend. And second of all of this is way easier on the actual machine that's going to run all of this stuff. In a VM, you build all your own headers.
Bear whale snake.
No more because the thing running inside a container is itself pretty normal. The only difference using the table related to this process with a different namespace. Also, if two containers have a shared layer in their disk system that contains a library that the application makes use of, the kernel knows that that's the same library.
Bear whale snake.
Libraries that are not containers, which is to share the same memory space.
It's gotta be bear whale snake.
Library in memory all at once. If something tries to modify in memory that library once it's loaded, then the kernel
Snake.
copy on modify tree. So the process is making modifications.
Snake.
So this is the prime reason that containers have really taken off. They're a lot more resource efficient.
Fire.
More efficient for people trying to run these systems. As if we just want things like a web server or memcache, we don't have to do this whole thing from scratch. We can either use a pre-built image as is, or we can use it as the layer for the basic container we're going to build our own changes and modifications. Once we build that, we put it in our own repository so we can use it on our servers. And this is what I'm going to do. I'm going to take a basic Linux image and I'm going to create an image with DOS-MU in it, and then I'll take that DOS-MU image and then I'll extend that further to add software. Now, DOS-MU being a fairly commonly used thing, there is a reasonable chance that there are out there that I can just use with either no modifications or just tinker a bit for my use case. So that's where I went to look up
Bird.
an image that was already built based off Debian with DOS M that went well.
Bird.
Quite nicely for me. And that's when I spotted something interesting. The same user created a DOS M base image.
Bird.
Also created an image that extended it DOS M.
Dragon.
Some PBS software in it. Suddenly, this
Fire.
not simpler. Now,
Bird, dragon, dog. Bird, dragon, dog.
that's the frighteningly modern part, right? Please say that's the frighteningly modern part. Well, no, it turns out we've got a lot more frighteningly modern to go. You see, I'm trying to build a place on a cloud-type enterprise system. And that you just plain Docker presents us with a problem. In plain Docker,
What?
we, log on to a machine.
Where's the ivory claw?
And any other containers we need. We don't have to set up any shared storage those containers need.
What?
Networking stuff, etc. The problem with that is, though, if it's just one machine, if we're building this as a problem,
What?
we can't be in a situation where one machine dies, no matter how reliable that machine is, the whole service is equipment. And once we know we want to run it on multiple machines, all this hand logging into boxes and setting up Docker containers and trying to do load balances and other stuff like that as well, just not going to cut it, because we need to be able to take nodes in and out of this system. We need to be able to take nodes down for maintenance, and other nodes when we need more capacity, or just the original hardware to getting it on. What we really need is an orchestration system that sets up all these container storers. You can handle nodes being that. Well, luckily that system exists. It's called Kubernetes, or the American Kubernetes. If you're already aware of Kubernetes, sounds a different way. Well, for the rest of the video, I'm going to pronounce Kubernetes, and you're going to have to make peace with that fact. Now, Kubernetes is a system that can install multiple nodes. But for the purposes of this video, and for the sake of my electricity bill, I'm just going to set it up and install it on this one HP node here. I'll go over the details of the HP node later. But just bear in mind throughout the whole of this conversation about Kubernetes, it's a multi-node system. Normally you'd have lots of nodes in Kubernetes cluster. You have to build everything, assuming that there are going to be multiple nodes. So at some point, I might want to add another node to this PBS service and take some nodes out, for example. Now, what Kubernetes lets us do is specify what we want the system to end up looking like. We don't tell Kubernetes how to do that. We don't tell it which nodes it's going to put containers on. We just specify how many containers we would like, the spec of those containers. They might have some file storage linked up to them, or in fact the same file storage linked up to multiple containers in some instances. And which containers we would like to be talked to. All we do is specify how. Kubernetes how. If it's a and then it gets on right when it's out first. You may have to use resources, well it works out. And that's also why later on we'll see you specify the amount of memory and RAM.
I gotta go to Solitude.
Kubernetes knows how much it's
Right? Where I gotta go? Where do I gotta go? I gotta go to Solitude. I gotta go to Fulgenthur.
Let's not get to this service.
Why do I gotta go to Fulgenthur?
Overview of the steps I took to get the
Investigate the golden merchant.
by any stretch of the imagination. I mean, this video is going to be long enough about doing that. If you want to find a tutorial on any of these steps that I do, well, YouTube's absolutely ridiculous. If you are interested, however, in setting up your own Kubernetes cluster, this will at least give you an overview of the steps that are involved, even with all the detail as to exactly how to do it. It's not really presented in this thing. Right, so we take our HPPL 380 and we power it up, and the first thing we do is go into its provisioning section through BIOS next step, we're about to use something called Helm. Helm is a system for installing stuff into a Kubernetes cluster. Ordinarily, we specify what Kubernetes to build.
Why is there a bush on the bridge?
Helm gives you a way of grouping pushing those YAML files together and then installing the project. No,
Fucking.
it also does a bit more.
Fucking.
Gives a bit of template.
Why are they letting this fucking place go to shit? Letting fucking plants grow in the road? What the hell?
We're going to install something called Argo CD.
This needs to be maintained.
Extraction I'm going to introduce. Argo, once it's installed, connects onto a Git repository. And in that Git repository, we've got a number of files, again, or in YAML, that define the applications we'd like to have installed on our Kubernetes cluster. And those application definitions can be pretty simple. It can just be, hey, I want an application called Dave, I want it to go into
Who are you?
space, and I want it to
Hello.
Milk drinker like you doing out
the
here.
thing is here,
Go home,
once
Jim,
you
mother.
commit one of these to Git,
Why?
push it,
What are you
Helm
gonna
knows
do?
what you've done,
Cry?
apply those changes to Kubernetes. Also, if you happen to have access to the Kubernetes cluster and
I don't have to take that from you.
Well, Argo will state different from source. And convert those changes into Kubernetes back.
Uh-oh.
That way, any
Uh-oh.
that will be installed in Git. We also use whoever has access to the cluster doesn't have to be the same person that's committing things in. And it also makes sure that you change the role of back-end communication as well.
River of safety. Give me your safety.
I'm now going to introduce the last bit of technology in this step. Now, if you remember earlier, I said that we were going to run multiple containers multi-run system inside there. And that all these containers will have a shared bit of filing system that contains the multi-run data files. After all, it's not like this thing has an SQL backend, it's going to build. Now, in order to do this, we use a system to spot any node that died. So we can't have files dependent on any node that's stay alive. If you remember, building this system, even though I'm just going to use the one node to start with, electricity bills. So this is where we're going to use something called a set. Set provides a way of multiple storage unit. Now that block storage is what gives us the nature of this filing system. Set has what's known as OSD, object storage unit. And those can be placed on a whole bunch of computers. When you create a filing system on top of that, you tell it how many copies you want that to be. i.e. the data must be installed in at least 3 places. Zach then has what's known as a crush map that works out where it can store that data. You can say another. So complicated. What you can have is that every server well, Zach will then try and make that into 3 separate racks based on the crush map. If there aren't 3 separate racks per server, well, then it can try and put it all in different terms at the very least and try and get at least 1 copy that you can. If you have to do the setup that high, well, then there's only 1 server and 1 rack, so it will just try and put it on 3 separate disks. If I didn't have a node, well, then it would try and move the data around so the data was at least on 1 server. And if I got to the point where there were multiple servers, suddenly I gave multiple racks of servers, well, then it would try and distribute the data across multiple racks. Now, see, there is a perfect node. An operator just sits there waiting for you to define some objects in Kubernetes that tells it what you want. Once those objects are defined, Brooke goes ahead and builds that setup for you. So we're going to use Argo to install Brooke, and then we're going to make ourselves the help jobs that Argo can install to tell Brooke what it would like. And in those help jobs, we specify things like how many monitor instances we would like. Except the monitor is the thing that knows where everything is stored. It maintains the index.
You're interfering with official form or business.
Which file system, for example, and on
I am a former justiciar of important business
and
that
if
you
an OSD
are
ever goes away
interfering
or
with.
a new one appears, The monitors are responsible for...
We are special envoys of the Aldmeri Dominion, the rightful rulers of Tamriel. If you'd like, I can show you why. If you're smart, you'll walk away.
The reason we need a one is because when we set up a Ceph filing system...
That we are superior to men is an established fact. For example, take this belief in Talos, the ninth divine. Certainly you don't believe such things. Or perhaps there's something you'd like to confess.
Backflushing it to an OSD. Move the monitor telling it which OSD to write to. The final bit we do is we finally need to tell it which disks in the system.
You can worship whatever gods you like.
Now,
but Talos is a man, and only a heretic would think otherwise. And so you will die a heretic's death.
This doesn't tell you which disks we want an OSD setting up for, and once that's synced by Argo, then you protocol takes that up and starts setting up OSD for each one of these disks, handling the formatting and everything, until eventually they come up with working. We now have a solution where if we add another node, this storage will be available to it, but also on that new node we'll specify the disks that are on there, what OSD is for, and Brookwood add them all into the cluster and start replicating copies of it out to that node already. At which point, if we lost the original node, no big deal. We can still keep picking all the filing systems available right at the final bit is to set up something called CSI, Container Storage Interface. Kubernetes has a series of plugins available to it.
Alright, I know you're valuable.
Lots of different storage.
Got you like a fish.
Each one for Seth. So again, we just make a little help chart for that, and Argo takes care of installing.
Yes, actually. You look like you're lousy with gold. I'm not going to...
What the fuck are you talking about?
We want a shared, multiple read, multiple write filing system, and...
No! What?
And allocated.
This is bullshit.
Look after those filing systems, and then we have storage that's ready to
Don't you walk away from me.
As a brief aside,
I can't even do any damage! What the fuck?
what this allows you to do is
How do I look like I'm lousy with gold, you dumb fucking bitch?
application or shut down, which is a pretty big deal if you well, it should be noted that this is not the same as backup. You can't revert it back to how it was a couple of hours ago to a remote replicated copy. This is more about being able to migrate workloads between data centers. While we're on the topic
Fuck
of
you.
Another application we'll throw in via Argo is Valero, our backup tool. Now this helm job happens to be based on Valero backup application, but you'll also add
I'm not even talking to you.
backups as a default backup storage location, all of which will be specified as little values that you overriding the main chart in the definition file that Argo uses to install this thing. I bet you wish a complete backup solution was that simple for like everything else you've ever done, right? Right, let's get back to the history of bulletin boards for a minute or two. Some BBSs were allowed to have what was known as a door. This is where your BBS software would execute an external program, which would then be able to send and receive data to your user. So the door software would know which user it was, etc. Your BBS software would write to the disk what's known as a drop file that contains all that information the door application could open and read. Now, the most common use for doors was games.
How do I access my favorites?
Or at least ASCII-based, and be able to work with the kind of latency you get over a modem on a public telephone line. So common things you'd see is things like text-to-adventure games, but you'd also see MUDs, multi-user dungeons.
What?
Like
I already did that.
I mean, with multiple people all being in the same world and being able to talk and interact with each other, or hit each other with pointed sticks. But you'd also see games like Trade Wars that is text-based, definitely not a text-adventure game. And for those who are playing these games, this would be their first experience of online gameplay, where you get to play with other people over your modem. Admittedly, not a lot of people at once.
I want to know where you guys are going.
That's one of them, we really have one or two, four or five, and not everyone lining up wants to play the same role. So what you do local call. So although calling your local call is cheaper than calling one that wasn't in the same area as you, it still costs money. So when school let you use the program was quite frequently when online gameplay would take place. Later on, you'd also get the concept of a program, which is a door that your BBS software could run, that would effectively telnet over to another machine where the game would run. Now, that wasn't typically telnet to a machine over the internet. You don't have common access to the internet yet, but you would find it on larger bulletin boards that have outgrown what a single computer could do, and where there would be, say, for example, multiple PCs, which are set as modems, would share data files using a file server, something like NetWare or Fantastic or LAN Manager. You would then see these link doors essentially telnetting from whichever machine you dialed in, whichever shared host is running the game. This is much more of a big BBS thing than a small BBS thing. Although as you start getting that overlap between dial-up internet becoming a thing and BBS is still being in use, you would see doors becoming available to, again, link you to a game on a remote system, but you would also see some internet services being made available. For example, the local BBS I used to use offered an FTP door where you could essentially use that door, enter an FTP path for a file that you wanted off the internet, and that door would go grab the file and let you start line load everything down. For larger files, you could either leave the door or disconnect.
Hello? Can I be your
The
friend?
mercy of Stendarr does not extend to Daedra worshippers. You speak to a vigilant of Stendarr. Abort with any Daedra, and we will hunt you down. And any other abominations that prey on mortals. Vampires, werewolves, witches. But Daedra are the worst. Their callous disregard for our lives is abhorrent in the eyes of the God of Mercy.
So I can't remember my BBS username.
He is the God of Mercy, the patron of order and justice for all of Tamriel.
And that was my first internet.
We bring his compassion where none can be found, by cleansing all those who would offend his children.
So this is towards
Stendarr be with you.
away now.
I didn't even talk to you. Yeah, you fucking do your little fucking run. Your little fucking I poop my pants ass run. Fucking little piss off. Hi. Hello, city guard. How are you doing? City guard.
Now, you probably noticed that I've looked set up and doing quite a lot of things. One of the things that's not doing yet is running our BBS. Now, if you remember earlier, sort of getting into the details on the helm chart, well, this is where we're going to do it. So we're going to define the helm chart that sets up our BBS containers. Now, again, this isn't a tutorial, this is just a whistle-stop tour of what I'm doing, because I'm guessing this is going to be a really long video when I edit it together. But I'm going to introduce the key concepts that you need to know. Just to make sense. The main unit of getting stuff done in BBS is what's known as a pod. You can think of a pod as a number of containers that are defined as running together on the same local host, which means they can have bits of shared storage between the containers, things like sockets, etc. And they have a number of parameters that they share, like a CPU or a RAM limit, and you can add some access control around the pod as well. So for our basic pod definition, we say things like we want to run the container, it's got our BBS image. We also define points in that container where we'd like to have some storage.
Atticus needs a wagon. He's got to take a wagon with him.
Storage, which can be read and written to by multiple pods at the same time. And that's so we can have that shared storage between the pods that our BBS files come within, so we can run more than one of these pods and handle multiple serial connections on each one. Like now, how do you tell me?
Come on, Mr. Wagon. We're going on an adventure. Over the waterfall, Mr. Wagon. Keep going. Keep going. You got the...
metal or of get inside the pods. So does our BBS for that matter. So for that we have a stateful set, a set of pods that have, a state. And if one of the stateful pods, the stateful set, gets murdered, well, it gets recreated and keeps back up to the exact set of storage that it was connected to before. Now the other thing we need to take care of is what gets on. So we'll set that is our BBS's data store. BBS that also uses file locking, so it's fine. We can have that mounted into each pod as shared storage with the session files in, and locking will work across them because CFFS maintains the whole POSIX semantics thing across multiple uses set filing system. So if you lock a file in one pod, it locks on another pod, even if that pod's on an entirely different computer. And this is not really a scaling issue because it's a DOS BBS and we're limited by the same file locking system for the actual BBS data files themselves. So back to the Kubernetes definition, we've got our stateful set with all our mounting, including the sessions directory. Other things we add are a service so that we can telnet into all the pods that we have running. Admittedly, we're just going to go for one in our stateful set. We also add a service for the VNC server, as that's acting as an X11 server, so all the DOS-MU instances have something they can draw on, because they expect there to be a screen. We also add a little secret, which I'm not going to show you, that sets the password for the VNC server, so that's managed in Kubernetes and not baked into the image. We also give this thing its own service account to run under Kubernetes so that it can have all its interactions with, and so it doesn't gain any privileges that we don't want it to. And once Argo gets that installed and running, there we go, we have our BBS that we can telnet into.
What?
Although that service